Hello, welcome to discussion section 2, and I'm going to be explaining how to solve certain heuristic problems. Okay, so looking at question 1, we have a agent that's a car, and it can do actions go in 4 directions, or it can accelerate or decelerate, which is a fast or a slow action. So now we would like to see what its state representation is going to be like. Let's take a look at question A. So question A is asking for the size of the state space. We know that there is n by n possible positions that it can be. And then we also know that it can face 4 directions. We also know that it has a lot of possible speeds that it can be at. And what are they? They're 0 all the way to Vmax. So now that we have all this information, we can calculate the size of the state space. So how do we do this? We see all combinations of it, we multiply them together, and we will get 4 times mn times 1 plus Vmax. That's our solution to part A. Okay, moving on to part B. It's asking us to identify if a certain heuristic is admissible. So then what they want us to identify is the Manhattan distance. So is the Manhattan distance admissible? In some of our problems we saw that they were, but for example, Pac-Man search. But in this case it is actually not admissible, because of the situation where this agent, the car, can both accelerate and decelerate. For example, if we had a situation where we saw a long corridor with the agent 6 blocks away from the goal. We have the agent here, it is facing in this direction, and it wants to get to the goal. Assume that it had a velocity 4 right now. It can choose a few slow actions such that it gets to the goal in time. Now let's calculate how many it is. If we choose 1 slow action, it's going to end up here. It does another slow action, it's going to end up here. Takes another slow action, it ends up at the goal. And then takes a slow action, it ends up with velocity 0. So how many steps did that take? That only took 3. Versus the Manhattan distance. The Manhattan distance was 6, which is not less than or equal to 3. So in this case, Manhattan distance is not admissible. Now, moving on, let's look at question 3. We want to identify now admissible heuristics that are non-trivial. So let's start with slightly easier ones. So obviously, because we have directions in this case, we have to at least be facing the goal. So one heuristic that is admissible is the number of turns the agent has to make before it faces the goal. So it will take at least that many actions to get to the goal. Now, let's make one that's slightly better than that. Let's see, for example, we had an issue with our previous heuristic, which was that it overestimated because it did not account for speed. So what can we do? We can directly account for it. We can have a d Manhattan distance divided by the maximum velocity, which will always be at least an underestimate of the true amount of time steps required to get to the goal. Okay, so now we can have a few more things that are better. For example, we can have some combination of how many turns it takes, and the how many, and the distance divided by Manhattan distance, by the maximum velocity. But what if instead we also can take into consideration the deceleration? Then we're going to have a strictly better heuristic than either of the previous two. So this would be similar to the amount of time steps that it takes to deaccelerate to 0 is going to be Vmax time steps. How much is that? We have, we will be at Vmax minus 1 plus Vmax minus 2 plus 1 distance away. I'm going to call this decelerate. And then the amount of speed, and we can assume that we're going to just go at max speed for the rest of the time. So how far we do that? We go at max speed. I'm going to call this dmax. This is going to be the Manhattan distance minus the deceleration distance. So then our heuristic then becomes we're going to keep it, we have a situation where if it's not far enough, then we're just going to keep it at d Manhattan distance divided by Vmax. And this is if the Manhattan distance is less than or equal to the deceleration distance. But if it is greater, then we can do the thing that we want, which is d Manhattan distance, Dmax distance divided by Vmax, plus the amount of steps it takes to decelerate, which we know is Vmax steps. So we can see that the third heuristic here is strictly better than our first one, is the best, because it will always be greater than or equal to this one, which is better or equal than this one. So this we call dominating heuristics. Okay, now we're gonna go over some conceptual questions. Looking at part D, if we use an inadmissible heuristic in A-star graph search, would the search be complete? So we can think about that. If we had inadmissible and we're doing graph search, it will eventually hit all the nodes as long as the heuristic is not unbounded. So will it be complete? Yes, because it will eventually find a solution should it exist. However, now the question is, will it be optimal? And then an inadmissible heuristic will not guarantee optimality because it will make us think that a state that's very far away from the goal is actually very good and vice versa. So this is false. Okay, so now that we have explored an inadmissible heuristic, let's take a look at admissible heuristics. So now we're going to have the same question. If we have an admissible heuristic in A-star graph search, is it guaranteed to return an optimal solution? Let's think about that. So for admissible heuristics, all it guarantees is optimality on tree search. So for the part 1, admissible, this is no, because we're saying it's graph search, not tree search. So this implies that we need a stronger constraint on the heuristic, which is what we call consistent. So if it is consistent, then it will guarantee optimality on graph search. For the next part, this is more conceptual. We kind of hinted at the answer already. If you were using A-star tree search instead of A-star graph search, then the admissible heuristic will guarantee optimality based off of the definition. And it will a consistent heuristic guarantee optimality? It will indeed as well, because we have shown in class that a consistent heuristic is necessarily admissible. So consistent will also give us the optimal solution. Okay, so moving on to the last part, it asks us, is there a advantage ever to using a potentially inadmissible heuristic over having an admissible one? So now we need to think of why we would potentially want admissible heuristics. A-star attempts to use heuristics to decrease the number of nodes that it evaluates, so that will save us time. But there's two parts. It needs to both explore the node and compute the heuristic. A potential advantage of an inadmissible heuristic is that it might be really fast to compute. It might be super simple, single calculation, not super accurate, but it will give us a very fast computational time, which will save on the amount of extra nodes that it might possibly have to expand. So
All right, question 2 is a CSP question called Trapped Pac-Man. So the setup for this is that Pac-Man is trapped between 6 corridors labeled 1 through 6. Each corridor leads either to a pit labeled P, a ghost labeled G, or an exit labeled E. So he wants to escape and find an exit. The one sign of what lies behind each corridor is a breeze that it produces. So a pit produces a strong breeze, an exit produces a weak breeze, and a ghost doesn't produce any breeze. Unfortunately, Pac-Man cannot directly measure the strength of the breeze at a single corridor, because that would be too easy. Instead, he can stand between 2 adjacent corridors and feel the max of the 2 breezes produced by those corridors. So if you were to stand between a pit and an exit, he's going to sense a strong breeze, because the strong breeze is produced by the pit. Likewise, between an exit and a ghost, he'll sense a weak breeze, because the exit produces the weak breeze. Also, Pac-Man knows that for any 2 adjacent corridors, they can't both be exits. So for instance, if corridor 1 was an exit, then we know that corridors 2 and 6 cannot also be exits, because that would violate that condition. So if we look at the diagram here, we see some S's and W's, each at the intersection of 2 of those corridors. So those are Pac-Man's actual measurements here. So that's the setup of the problem. To model this as a CSP, we're going to treat each corridor as a variable xi. So corridor 1 is x1, etc. Each of those is going to have domain p, g, and e, because those are the possible values that they could have, as in those are the possible things that could be behind the corridor. All right, from here, let's try to formulate the constraints of our CSP. So maybe let's start with this S here between corridors 1 and 2. So if we see an S here, so we have a strong breeze there, then we know that at least one of corridors 1 and 2 has to be a pit. Otherwise, we wouldn't be able to get a strong breeze there. So this is going to be a binary constraint, and let's call it x1 equals p or x2 equals p, right? Because this correctly captures the intuition here that one of these 2, or maybe both, has to be a pit to produce that. Going clockwise, we're going to see this W here between 2 and 3. So what can we conclude from this? At least one of these has to be an exit, because an exit produces a weak breeze, right? So we could say x2 equals exit, or x3 equals exit, right? We can also conclude something else, though. Could either of corridor 2 or 3 be a pit? The answer is no, because if they were, then we'd get a strong breeze, S, instead of the W. So we're going to have a unary constraint here, which is going to be x2 cannot be a pit, x3 can also not be a pit for that reason. Moving on clockwise, we have a W between 3 and 4, so we're going to do something similar. We're going to say x3 is an exit, or x4 is an exit, right? For the same reason as before. And then likewise, we get x4 cannot be a pit for the same reason as we had for 2 and 3. Moving on clockwise again, we have between 4 and 5, we have a strong breeze, so we can say x4 is a pit, or x5 is a pit. 5 and 6, you get the same deal. x5 is a pit, or x6 is a pit. And between 6 and 1, same thing. x6 is a pit, or x1 is a pit. Cool. Are we done yet? Not quite. We need to incorporate this constraint here, that 2 neighboring squares cannot both be exits, right? So one way to formulate this would probably be to say, for all indices I, j, if these 2 are adjacent, I and j, then we cannot have both xi and xj be exits, right? Then we cannot have xi be an exit and or xj, or sorry, and, yeah. Cannot have them both be exits. All right, so this is really going to produce several binary constraints. So those are all kind of lumped into the binary constraints. So I think at this point we have correctly formulated our constraints. Now let's move on to part B. Suppose we assign x1 to be E, so an exit. Then let's perform forward checking after this assignment while also enforcing unary constraints. let's first do the unary constraints, because that's pretty easy, right? So x2, x3, and x4 cannot be pits. So we can just cross these guys off. All right, from there, let's look at the binary constraints. So if x1 is e, which variables share a constraint with x1? Let's see. So x2 does, because x1 has to be a pit, or x2 has to be a pit, right? Because we sensed a strong breeze here. So that means that at least one of x1 and x2 has to be a pit. So if x1 is not the pit, then x2 would have to be a pit, but that doesn't work here. So these variables, or these possible assignments, are off, because if any of those were there, that would violate the constraint that x1 equals p or x2 equals p. So as a side note, at this point we can already tell that assigning x1 to be e is not going to work. It's not possible. But let's keep on going for the sake of completing and demonstrating this algorithm. So x3 doesn't share any constraints with x1, nor does x4 or x5, but x6 does. So just like x2, between 6 and 1 we have a strong breeze. So we know that at least one of those two has to be a pit, which is represented by this constraint also. So we know that x6 has to be a pit. In other words, these possible assignments will not work. So this is going to be the outcome of forward checking. All right, so let's suppose we run forward checking with some other kind of assignment, and at some point we get the following set of possible assignments at this point. So according to MRV, which variable or variables should the solver assign first? So remember that MRV is minimum remaining values. So which variables have the fewest remaining values? So if we count, that's just going to be x1 and x5, because those have 1. All the others have 2 or 3. So x1 or x5 would both be valid answers. At this point, it comes up to however you're going to do tie breaking. So that's the answer for this one. Now moving on to part D. Let's assume that Pac-Man knows that x6 is a ghost, so G. So let's try to list the solutions of the CSP given this information. So we know x6 equals ghost. So if we recall from before, between 6 and 1 we saw a strong breeze, which means one of those two has to be a pit. So if 6 isn't the pit, we know that x1 has to be the pit. Likewise, between 6 and 5 we also saw a strong breeze. So x5 has to be a pit by the same logic. From here, we're left with 2, 3, and 4 unassigned. We know they can't be pits because of our unary constraints. So each of them, x2, x3, and x4, are going to take values in E or G at this point. Exit or goal, or sorry, exit or ghost. So we can start by assigning x2 equals E. What is going to happen from here? Well, the first thing we can say is that x3 cannot also be E. Remember that no two adjacent corridors can both have exits. So we know that x3 has to be a ghost. But knowing that, remember that between x3 and x4, we had a breeze that was weak. So a weak breeze must be produced by an exit. So if x3 isn't the exit, then we have to say x4 is the exit, right? Okay, so that was if we started with x2 being E. But what if we say x2 equals G instead? Okay, so then what do we get from here? Could x3 also be G? The answer is no, because between 2 and 3, remember, we saw a weak breeze. So at least one of those two has to be an exit. But if x2 isn't the exit, it has to be x3, right? By the same logic as before, we can't have x3 and x4 both be exits. So we get x4 equals ghost. So these are the only two possibilities given this stuff that we started with, which is deterministic. Like, these have to be true. So if we were to list them out, we would say 1 through 6, we would have P, E, G, E, P, G. So that's this first one over here. And then the second one would be P, and then x2 is G instead. G, E, back to G, and then finally P, G, corresponding to the second one. So these are the two solutions to the CSP, given that x6 is G. All right, let's move on to question 3, which is heuristics. So recall the corners problem from project 1. There are 4 corners, and for each corner, there's going to be a food pellet in that corner. So Pac-Man needs to navigate the maze to hit each of those corners and eat each of those corner food pellets. So that is the setup of the problem. Now, in part A, we're going to look at several heuristics, and we're going to decide whether or not they are admissible. And for the ones that are not admissible, try to find a concrete counterexample showing that at some state, it's not admissible, as in at some state, the heuristic value is going to be an overestimate of the actual minimum cost to get to the goal state. All right, so let's look at number 1. So H1 is the maze distance to the nearest food pellet. And if no food pellets remain, then the heuristic value is just 0. So consider that if there are food pellets remaining, you have to eventually go and get them before you're going to be done. So if you're going to go and get them, you have to at least travel to the nearest one. If you travel to a further one, then you're going even farther than the maze distance to the nearest food pellet. So for that reason, this heuristic is admissible because it is always going to be an underestimate of the actual cost to finish the entire thing. H2 is the number of uneaten food pellets remaining. So this one is actually also going to be admissible, and the reason for that is if there are K food pellets remaining that you haven't eaten yet, each food pellet is in a different location. So in any given move, you can only eat at most 1 food pellet. So you're always going to move at least K spaces if there's K food pellets remaining. Hence, it's always going to be an underestimate of the number of moves you need to make to finish this problem. Moving on, we have H3, which is going to be the sum of H1 and H2 as described here. So this one's actually not admissible, and let's go over the reason why. So we need to find a concrete counterexample, right? So for a lot of things like this, you want to find a sort of minimal counterexample, or the simplest possible thing to reason about. For almost all the cases you're going to see in this class, if you have to decide if something's admissible or not, you'll be able to show it's not admissible, if that's the case, with a very simple counterexample. So the advantage for this is that it's usually pretty easy to reason about. So what is like the simplest thing we could think of? Maybe there's a grid like this, something like this, right? And there's a food pellet in this corner, and then Pac-Man is right here, right? So very simple. In this case, H1 is going to be 1 because the maze distance to the nearest food pellet is 1. H2 is also going to be 1 because there's 1 uneaten remaining. But if you add them up, you get 2. The problem with this is that it only takes 1 move to finish it. So it's not going to work. Another nice kind of convenient way to think about it, or counterexample, would be like this. Maybe you have a very, very small grid, so very easy to reason about, something like this. So at this point, there are 3 food pellets remaining. So H2 is going to be 3, and the maze distance to the nearest one is 1. So H1 will be 1, therefore H3 will equal 4. But it only takes 3 moves to eat everything up. So both counterexamples would work, showing why H3 is not admissible. All right, moving on to H4, which is the absolute value of the difference between H1 and H2, where H1 and H2 are admissible. So in general, if H1 and H2 are admissible, then this is also going to be admissible. The reason for that is that admissible heuristics are non-negative. So if you take the difference and then take the absolute value, that is going to be at most the larger of the two. So since both of them are already admissible, that is going to be admissible. Finally, H5 is just taking the max of both heuristics. And again, in general, if both H1 and H2 are admissible, then the max of both of them is also going to be admissible. All right, so that is question A. Okay, part B. Pick one heuristic from the previous part that was unadmissible. Call it HK. So remember that the only thing that was not admissible was H3. So this guy is really just H3. And give the smallest constant epsilon, such that subtracting epsilon from all values of H3 are going to give you an admissible heuristic. And let's try to find out why. So recall that H3 equals H1 plus H2. So it's going to be the nearest food pellet distance, like maze distance to get there, plus the number of uneaten food pellets remaining. Okay, so let's play out a little experiment in our heads. Let's say there are some pellets remaining. So remember, H2 is exactly how many pellets remain. So if we want to finish, we have to eat all of them up. So you have to travel at least H1 to get to a food pellet, because remember, H1 is just the maze distance to the nearest food pellet, right? So let's say you do that. You travel to some pellet. It doesn't have to be H1, or the closest one corresponding to H1. But let's say you just go to a food pellet and then you eat it. So at that point, how many pellets remain? That's going to be H2 minus 1 remain after you eat the first one. After eating first, right? So at that point, you need to make at least H2 minus 1 more moves, right? Because that's the number of pellets you have to eat next. So recall that it took H1 moves at least to get to that first pellet, and then from there you'd have to have at least H2 minus 1 other moves to eat the other pellets. So how about H1 plus H2 minus 1? Because this is always going to be a lower bound on how many moves you need to make. So rearranging, we can just see that this is H3 minus 1, because H1 plus H2 is H3, and we're just subtracting 1 from that. So the answer is that epsilon equals 1 will work. All right, now let's move on to part C. Let Hi and Hj be two admissible heuristics, just in general, not just for this problem. And let H alpha be alpha times Hi plus 1 minus alpha times Hj. So alpha is just some number. What range of values for that number alpha will make this heuristic H sub alpha admissible, and provably so? So the answer is that alpha has to lie in the range 0 to 1 closed, so inclusive. Why is it inclusive? Because if it's 0, then it's just Hj, and if it's 1, then it's just Hi, both of which we already know are admissible. And if it's anything in the middle, then it's going to be less than or equal to the max over the 2, right? Because then we would have H alpha less than or equal to max Hi Hj. So if we have this value of alpha, then that implies that H alpha is less than or equal to the max of both. And we know that the max of two admissible heuristics is going to be admissible. So this guarantees it to be admissible. The next question is, can alpha be outside this range? The answer to that is no. Let's say we had like alpha equals, let's call it -1, right? So really H alpha is going to be, so this is a hypothetical scenario. Let's say H alpha in this case is going to be negative Hi plus 2 Hj, right? So we can find heuristics Hi and Hj that are admissible, but which will cause H alpha to break. So in this case, let's just say Hi equals 0, because the 0 heuristic is trivial, but it is technically admissible, because at that point, A star search is just going to do UCS. And then let's say Hj equals H star, which is the actual cost it takes. So 0 is sort of the lowest value your heuristic could be, and H star is sort of the highest value your heuristic could be. Otherwise, you would be overestimating. But then we see that H alpha is just going to be 2 times the actual cost to go, which is clearly an overestimate. So it doesn't work. Likewise, if alpha is greater than 1, you'll have the same problem. So this is the correct answer. Doesn't work. All right, so let's move on to part D. So in this setting, we have an arbitrary search problem. Our graph has some start state S and some goal state G. And let H star be the perfect heuristic as described before. It's going to be the actual distance from X to the goal G, the actual optimal distance. And then we're going to have epsilon be some positive number. So for each of these parts, we're going to define some kind of heuristic, and then we're going to try to find the range of possible values for the cost of a path that A star tree search would return using that heuristic. So let's unpack that a little bit. We're saying that for problem I, we're going to have H sub A, which is some heuristic. And we're going to run A star tree search using that heuristic. And then we're going to try to reason about, once A star search has found some sequence of nodes that is going to be what it thinks is the minimum cost path, we're going to try to reason about what is the length of that path. Like, what is the possible range of values for that path? So note that H star of S right here is the optimal path length from the start to the end, because that's how we defined H star. So right off the bat, let's think. If HA or HB or HC were ever admissible, right, then if we run A star tree search using that heuristic, we're going to get an optimal answer, right? So straight off the bat, we can say if HA is admissible, then we know that the answer is a single number. So it's just going to be H star of S, H star of S. Because we know that using A star with a admissible heuristic is always going to give us the right answer. So these problems are interesting because these heuristics turn out not necessarily to be admissible. So then we have to reason about how bad is it going to break our algorithm A star? Like, how bad is the result possibly going to be? So that's kind of what this is about. All right. One more thing that we can right off the bat say. For all these problems, we're returning a range between two values, right? A lower and a higher value. Is the lower value ever going to be less than H star of S? Let's think about that. The answer is no. Let's see what that would mean, right? Like, let's assume that somehow we did get something less than H star of S. That means that your algorithm, using this weird heuristic, somehow found a path from the start to the goal that was less than the optimal path cost. But this doesn't make sense. By definition, the optimal path cost is the least possible cost. So we know that the lower of the two numbers in the range is going to be at least H star of S. Just reasoning about the parameters of the problem. Okay, so let's actually start solving this. So the first one, HA, is going to be H0, which is some arbitrary admissible heuristic for all states, except at one unspecified state y, where HA of y is going to be equal to H0 of y, but plus some positive epsilon. So what can we say about this? First of all, it's not admissible, because if y were the goal state, then H0 of y plus epsilon, where epsilon is any positive number, would mean that HA of the goal state would be greater than 0, which is not allowed for an admissible heuristic. So we know it's not admissible. Let's think. So we need to find a lower bound and an upper bound. For a lower bound, that's going to be if A star returns a nice path with low cost. So what's the best case scenario here? Let's say the state y that is corrupted is a state we would never even visit anyways. So it doesn't really harm us to have it like this. For instance, what if it was start to some state A and then to the goal state, where this length is absurdly high, like 100. This is like 1 and like this is 1 or something. So if A is the state that is corrupted, like y in this case, if A is that state, then adding epsilon wouldn't break anything, because A star would still find the goal eventually. So we know that the lower bound is going to be H star of S. Lower bound H star of S. Because in some cases, it's very nice. Okay, so let's try to find an upper bound, which means we want to think about the worst case possible scenario. So what is the worst state y that could be corrupted? Probably one that's along some optimal path, because when something along the optimal path is distorted by epsilon, then the algorithm is going to keep that on the fringe for longer than it should be. So in the meantime, it's going to pop off other things, potentially popping off things on a suboptimal path that will eventually reach the goal before the algorithm pops off the optimal part, because we've deceived it by adding this epsilon. So let's try to construct a scenario like that. We have some start, and let's make two paths. One that goes through A to the goal, and one that goes through B to the goal. And let's say B is actually the good one, the optimal route, SBG. But we're going to have our heuristic, HA of B, going to be, let's say this is 1, so it's going to be 1 plus epsilon, which is an overestimate. And maybe call this like 4 or something. So then at this point, let's do S to A. Let's say this is also 4. And maybe we're going to say H of A at B, or oops, at A equals, let's say this equals 1 or something. Oops. And let's say the length from A to G is going to be 1 plus epsilon. Okay, so let's reason about what A star is going to do. So A star, starting from S, is going to look at A and B as its two possibilities. So it's going to add them onto the fringe. For A, it's going to put what value? It's going to do 4, the cost to get to A, plus the heuristic at A. 4 plus 1 equals 5. And for B, it's going to put 4 plus 1 plus epsilon equals 5 plus epsilon. So it's going to try to explore A first, right? And then from A, it's going to see the goal state at a cost of 4 plus 1 plus epsilon, right? So cost from S to A to the G is going to be 5 plus epsilon also, right? So then at this point, it comes down to tie breaking. How are we going to tie break? And if your tie breaking is wrong, then, or if your tie breaking is disadvantageous, not wrong, then you might just choose this one right here, which would lead you to the goal with a total cost of 5 plus epsilon, where the real optimal cost here was just 5. So the upper bound is going to be H star of S plus epsilon. So the answer is, making some space for myself, the answer is going to be H star of S and then H star of S plus epsilon. That is the answer for part 1. All right, let's move on to part 2. So HB of X is going to be H0 of X plus epsilon for all states X. So we're uniformly just adding the same small positive value to every state, or to the heuristic value H0 at every single state. So let's think about what this is going to do. So the way A star works is it's going to add stuff to a fringe and then pop them off based on the cost that it sees. So if everything's heuristic cost is bigger, then the order that A star does every single thing is going to be the same as the order that it does things without this plus epsilon term. That's the key insight here. If everything is changed by the same amount, then A star is going to do the exact same sequence of things. So in its intermediate steps, A star is not going to estimate things correctly because it's going to estimate using this wrong heuristic, H0x plus epsilon. But the order that it does things, and then hence the order that it reaches the goal and the path that is returned to get to the goal is going to be exactly the same as running A star with H0 without the epsilon. So the path that it returns is going to be the exact same path. Even though intermediate steps might look wrong, it'll finally come to the correct answer. So the answer here is actually just going to be H star of S, because it's always going to find the same path as H sub 0, which H sub 0 is actually going to find the optimal path because it is properly admissible. All right, let's move on to part 3 now. H sub C. So this is going to be H0 of X plus epsilon for all states except the goal state. So at the goal state, H sub C is going to be 0, just like H sub 0 should be. So it's very similar to part 2, except instead of incrementing everything by epsilon, it's everything except the goal state. In some cases, this might return the right path, I think, because using the same example as in part 1, like right here, where one way to get to the goal is just much better than the other way. Having this heuristic is not going to really mess things up too much because it's always going to find the right path for this graph anyways. So the lower bound is going to be H star of S. Very nice. So the tricky part is this upper bound. How are we going to reason about that? Let's consider the worst case thing here. let's say the goal state gets onto the fringe via a suboptimal path. And let's say the optimal path to the goal state is being added to the fringe, except at the last node, it has an epsilon misestimate, so it looks like epsilon worse than the suboptimal path. So at that point, the suboptimal path, which includes finishing at G, will get popped off and ruin the algorithm. So let's construct an example of exactly what that might look like. So let's again have S, go to A, go to G, and like this. So let's call this cost 3, call this cost 1, and call this cost 1. So the optimal here is actually to take the detour, to go through A, because that's cost 2. Now, let's say epsilon equals 1.01, so just a tiny bit bigger than 1. So let's say h sub c at this node A is going to be 2.01. Let's say h0 is 1 there, so add 1.01, you're going to get 2.01. All right, so at this point, what is A star going to see? It's going to estimate the total cost of A would be the cost to get to A, which is 1, and then it's going to add the heuristic, which is 2.01, so it's going to get 3.01. And then it's going to look at G, which is the other possibility from the start node, and then it's going to see that the total cost is 3 plus 0, so this is going to be 3. So we can see that at this point, A star is going to choose to go to the goal now. So it's going to end up with a cost of 3 for its total path, whereas the optimal cost was 2 to go from S to A to G. So the upper bound on exactly how bad the return path can be is going to be h star of S plus epsilon. If you change the numbers slightly, you can get it closer and closer to this value. And then up to tiebreaking, you can actually hit this value.